and start symbol, production, terminal and non-terminal. And with this, we saw how these symbols are being created or how these productions are being written with a start symbol of list or a head of list and the body of list plus digit and all. So how the things are being done, so that a simple parse tree probably we have seen yesterday in last class. With that, we'll continue for the today's class. Now we'll see in the today's class there is a term called the derivations. So when you have the terms, when you have the terminology, the not terminals, the non-terminals, and all those things that you've studied, then in the derivations of a context-free grammar or simple grammar, the derivation says that a grammar derives the strings by beginning with the start symbol. As we right now saw, the expression or the production always starts with the start symbol. And the tree or the, what do you say, the parse tree, it has at the root, the content is called the start symbol, right? And repeatedly replacing a non-terminal by the body of a production for that non-terminal. This is what we studied in the tree. So what we have, the start symbol remains at the root. Then for every what do you say, the positions of in the tree, you have the non-terminals, and finally it goes to the terminal nodes, or the body, the head remains at the root or at the non-core position, and the body remains at the left and the right of the subtree. This is how your parse tree was being generated. So now the terminal strings that can be derived from the start symbol form the language defined by the grammar. So what is a terminal string? By now we have studied about the numerical equation, like some 9 into 5 plus 2 something. But we didn't work with the strings, right? So now we will see how the strings are being generated or how the strings are taken care of to form the your parse tree or the regular context grammar. The language defined by the grammar of slide 20, we'll see what are the grammars that has been defined. In slide 20, this is the grammar. As I said, your production will look like, this is the whole production, where list is called the head and the right side of the production is called the body of the production. So we have the list like this, or the set of productions like this. We have 4 productions. One is the first one, having a positive sign between these two, then a negative one, a second one with a negative sign between these two. Then here the production head is the list and the body as the digit. And here these are the different kind of expressions, or you can say rules, that we followed here. So with these rules, whatever we studied, the language has been defined by the grammar of what we studied in slide 10, consists of lists of digits separated by plus and minus. This is what we studied. The list, and there is a plus or minus symbol, then there are certain digits. The 10 productions for the non-terminal digit allow it to stand for any of the terminals, that is 0 to 9. So 0 to 9 means you have the 10 productions, right? So all of these 10 digits for these non-terminals will allow to stand for any of these terminals. So from the production 3, that means the production 3 is least, we can have the form of digit. That is what is your production 3. So it says from the production 3, a single digit by itself is a list. That is what is mentioned. And production 1 and 2 express the rule that any list followed by a plus or minus sign and then another digit makes up a new list. You will see this. This says in 1 and 2, it says the first one and the second one, you have the list, the head can have the form of in another list having a plus sign or a minus sign and followed by a digit will form a new list here as the product. This is what we studied. And the third rule says list can have the form of the digits and where the digit can have any of the value between 0 to 9. This is what we studied. The same thing is being explained here. So from production 3, a single digit by itself is a list. For 1 and 2, express the rule that any list followed by a plus or minus sign and then another digit makes up a new list. This is what we studied. Now what it says, production 1 and 4 are all we need to define the desired language. What is 1? Production 1 says list is list. List can have the form of list plus your digit. And 4 says the digit can have any value between 0 to 9. Right? So with this now we'll see, for an example, we can deduce that 9 minus 5 plus 2 is a list. How we'll see? We'll see how this can be treated as a list or this can be treated as a product. Now 9 is a list by production 3. Right? Since 9 is a digit, because that is what it says, list can have the form of digit. So remember slide number 20. So 9 can be a list because it is a digit. Now 9 minus 5 is a list by production 2. What production 2 says? Production 2 says the list can be the list minus a digit. So if 9 is a list and minus 5 is a digit, so 9 minus 5 can be also a list as per the rule. So since 9 is a list and 5 is a digit, as I said, that means the list can be a list minus a digit. So this is also becomes a now new list. Now the whole thing 9 minus 5 plus 2 is also a list by production 1 because 9 minus 5 has been proved as a list here and 2 is a digit. So list plus 2 plus a digit becomes another list. So now with this, it has been proved that 9 minus 5 plus 2 is a list. So you agree to this now? What we have? Initially it says 9 as per the rule 3 is a digit. So a list can have the form of a digit. So 9 itself is a digit. Then when 9 is subtracted by 5, it becomes another list. Because as per the rule 2, it says list can have the form of list minus a digit. So if 9 is a list, list minus 5 will be another list. And the whole thing is a new list that will be added with another digit 2. So 9 minus 5 plus 2 becomes another list. This is how you can prove that you can deduce that your expression is nothing but a list.
Excuse me, ma'am.
Yeah.
Excuse me, ma'am.
Yeah.
Actually, like previously, you have been told that this expression will be evaluated by the by using lists and digits. So actually, what we are doing, like we are again building a list. So how it can evaluate?
Okay, can you repeat your question?
Actually, we are just evaluating that expression, okay? And then you just again put that all in a list.
We are not evaluating the list, or you are not evaluating the equation. What we are seeing is we are going to make a parse tree, right? So we are doing the scanning of each character, correct?
Yeah, ma'am.
Do you want me to go to the slide number 20?
That one where you have shown productions.
Huh?
Yeah, as you wish, ma'am.
Or you want to explain this one here only?
Ma'am, as per your choice.
Okay. So what exactly we are doing is the parser or the lexical analysis. What it does is it scans every character, right? So now when it scans every character, the next step is to make a parse tree. Okay. So now to make a parse tree, computer has to be programmed, has to be instructed how it will handle every digit or every expression. How the computer will come to know that one is a it's a numerical value, it's a digit, it's a expression, it's a string. How it will know? It has to be programmed. It has to be instructed accordingly, right?
Yeah.
So now let us say this input has been given to the computer. 9 minus 5 plus 2. The computer doesn't understand anything. But the set of rules that it has to be followed by the computer is it understands that I have to make a production, right? And the production says I should have a head in the left side, I should have a body in the right side. That is how the computer understands. Keep yourself in the position of a computer or in a lexical analyzer. So how you will analyze? You have no idea of anything. Whatever you have given to you or whatever instruction given to you is, there is a production, there will be a production, head in the left side, there would be a body in the right side. The left side is termed as a list. The right side can be a list plus a digit, a list minus a digit. It can be only a digit. And you have been instructed that what do you mean by digit? Digit is nothing but 0 to 9.
Yeah.
That only that much is given to you. Digit is 0 to 9, right? Now, this digit go from the backtracking from fourth to first. I'm going now. I'm going to let me go to the fourth 20 slide. That is here. Okay. Now let us say these are the 4 instructions given to you. Imagine yourself as the lexical analyzer. You will be said that list is list plus digit, list is list minus digit, list is digit, and digit is any of these values, right? So now you start from the fourth one. You know that 0, 1, 2, 3, 5 can be any of this value can be a digit. This is defined, given to me. So now first 9 comes to you, right? So when 9 comes to you, you know that 9, the digit can have the form of 9. That means 9 is a digit. You understood that?
Yeah,
so as a computer, you understand 9 is a digit. Then when this statement, the third statement comes, it says that this production says that the list can have a value of digit, right? That means your 9 digit has come here now. So that 9 you can say as a list now. Can you say or not? You can
yes,
say, right? Okay. So that means 9 has initially considered as a digit. Now digit is being considered as a list. So you understand that now 9 is a list, right?
So ma'am, basically we are here working to prove that whatever the string we have taken is a list at the end.
Yes. You have to understood how you deduce a formula, how you deduce, how the computer scans everything. This is just a simple example where I have given only the integers, but there will be some instructions where there will be strings, there will be different operators, many things will be there. So right, so that can understand how it has to handle, and it will distinguish whether it is a production, what is a body, what is a head, what is a digit, what is a list, what is a string. Everything will be identified. But to identify those things, the computer there should be a basic rule. That is what is a compiler design. When we say the compiler converts it or translates the program to a machine language, it should know what is the program you are writing. you write something 9 minus 5 plus 2, what the computer will understand out of that? Imagine, it cannot understand, right? What it understand, it has its own function, own programming or own understanding. So your program has to be put into that format, then only it can identify each of these characters, and accordingly it will transfer or translate to the machine language or to the assembly language, right? So what we are studying is, we are just trying to explain the computer how you identify each of the things and put them into a frame or put them into a formula so that you can extract or you can understand what is that.
Okay, ma'am.
Right? So now it makes clear?
Yeah, sure.
Okay. So, okay. So now the 9 minus 5 plus 2, the whole thing has been deduced as a single list. So now if I add anything to 9 minus 5 plus 2, if that comes under a digit, then that can be also considered as a list, or that can be considered as a production. Why I am making a production? Because if I have the production, I can make the parse tree. If you remember the yesterday's class, in a production, there will be a start, and start is always the root of your tree, right? Then you go for the head as the left and the body as the right. So everything has to be in the format of a production. So production format is there, then the parse tree can be built. So that is what is the intention of making the things in the form of a production. And if you want to put in a production, it has to be in the form of a list, can have the form of list word plus digit, or all those formula, those 4 formula has to be taken care of. Then only we can say that our list is generated or list is framed, and that list can be converted to a parse tree. This is what is, as I said yesterday, this is what is the parse tree now. Now your list has the form of A, can have the form of X, Y, Z. So here A will be the root or the start symbol, and X, Y, Z can be the children of that. That is what is the target of making a list. So this is the head and this is the body of the production. So if non-terminal A has a production like this, then a parse tree may have an interior node labeled with A, any interior, it could be any interior node with A, with the 3 children X, Y, and Z from left to right. This is what is the objective. So to make this parse tree, we have to make this production. To make the production, we have to understand what are the content or what are the formula or base rules in which the equation can be put to get a production. That is what is the whole objective of lexical analysis. So now this probably we studied, this probably we studied in the last class. It's formally, it is a given context-free grammar. A parse tree, according to the grammar, is a tree with the following properties. What are the properties? The root is labeled by the start symbol, as we have decided or studied. Each leaf is labeled by a terminal, or if there is no terminal, it will be as a null tree, or you can say as an epsilon. And each interior node is labeled by a non-terminal. So your interior nodes are labeled by non-terminals, your leaf nodes are labeled by terminals, and that is how your parse tree is constructed from the production. So if A is the non-terminal, labeling some interior node x1 to up to xn are the labels of the children of that node from left to right, then there must be a production. A can have the form of x1 to xn. This is the production formula. To have this, we did all those things. In case of a special case, if A has no terminal node, or if it says A can have the form of non-terminal or A can have epsilon in a production, then a node labeled A may have a single child labeled epsilon. Doesn't have any other child. It has got only one child, and that child is nothing but your epsilon. So now you can have the derivation of this 9 minus 5 plus 2 as we saw. Your first is the least. Least is taken as the start symbol in your production. And then what it says, list can have the form of list plus digit. Do you remember that? So as per the equation 1. So it says first one is list plus digit. The first rule. What the second rule says? List can have the form of list minus digit. So here is the list minus the second child, and the third child is the digit. Right? And the third rule says list can have the form of a digit. So this is what? List, only one child, digit. And digit can have in the form of any value 0 to 9. So here comes 9. Now here also there is a digit. So this digit can have a value of 5. Here also there is another digit. This can have the value of 2. So now you understand why this is in the form of, why the 9 minus 5 plus 2 was brought to the form of a list, so that you can, not you, the lexical analyzer can design this parse tree. And this is required for the lexical analyzer. Here you see every single character is being identified or scanned. Then it can say 9 is a digit, minus is a list, 5 is a digit, plus is a list, 2 is a digit. So accordingly it will be interpreted, or your intermediate code will be generated. This is what was the objective for which we studied. Now, each node in the tree is labeled by a grammar symbol, as we saw. An interior node and its children correspond to a production. This is what we studied. If we say this, if this is an interior node and its children are list, so this is a production. List can have the form of list minus digit is a production. Similarly, list can have the value of digit is a production. Similarly, digit can have the value of form of a 9. This is also a production. So this is what are the different productions are framed here. Now the interior node corresponds to the head of the production. As I said, left side is the head, and the children to the body, because children remains in the right side, so they become the body of the production. The root is labeled list. That is the start symbol. So the root of the tree is the list as the start symbol. The start symbol of the grammar in slide 20 that we saw in the start symbol. The children of the root are labeled from left to right. In the root, all the children are labeled from the left to right, as we saw the list, plus, and the digit. For example, list can have the form of list plus digit. That's what I said. List can have the form of list plus digit. So all this body, or they are designed, or they have been constructed as the children of the head or the start symbol list. The left child of the root is similar to the root with a child labeled minus instead of a plus. This is the left child, and this is the same frame as the list, but only difference is here in the root there is a plus sign, but here in the production there is a minus sign. That is the only difference. Otherwise, this remains same as the root tree or the first production, you can say. Then the three nodes labeled the digit each have one child that is labeled by a digit. As I said, you'll see all the three digits, here one, and here one. They are labeled with the three numerical values or three digits, you can say. From left to right, the leaves of the parse tree. Parse tree. What do you mean by leaves of the parse tree? What is the leaf of a tree? The leaf of the tree is the last node or the last child who doesn't have another child, right? So that is what is the last node of a tree. So when there are multiple leaves are there, we say they are the leaves of the tree. So the leaves of the parse tree form the yield of the tree, means outcome of the tree, which is the string generated or derived from the non-terminal at the root of the parse tree. So what is the yield here? You can see 9 minus 5 plus 2. This is the yield of the tree, means this is the outcome of the tree. So that is what it says. From left to right, the leaves of the parse tree. What are the leaves of the parse tree? This is a leaf, right? This is a leaf, this is a leaf, this is a leaf, this is a leaf, and this is a leaf. So all these leaves of the parse tree form the yield of the tree, which is the string generated or derived from the non-terminal at the root of the parse tree. So here the yield is 9 minus 5 plus 2. This is what is the set of leaf nodes of the tree. So another definition of the language generated by a grammar is as the set of strings that can be generated by some parse tree. Here what we saw, this is what is the yield or what is generated is all the numericals, right? The equation, or you can say the digital values, numerical values. But this is also true that you can also have the strings that can be generated by this. So the process of finding a parse tree for a given string of terminals is called parsing that string. So now we did the parsing numericals or parsing an equation, but this can also be used for parsing the strings. We'll see in later subsequently what the string is and how the string is also being parsed. So now, before going to that, we'll see something called the ambiguity. What is an ambiguity? Ambiguity means the what do you say, discrepancy. Any discrepancy or any loophole that you can see in the solution. That is what is the ambiguity. So what the ambiguity is? A grammar can have more than one parse tree generating a given string of terminals. What it says, now for this symbol 9 minus 5 plus 2, we made one parse tree. It says that for the same equation, we can have multiple parse trees also. That means if we understand the equation in a different way, we can build another parse tree for that. And that is what is an ambiguous situation. So a grammar can have more than one parse tree generating a given string of terminals. And such a grammar is called the ambiguous. This is what is the ambiguous means there is a conflict. There is something undesirable happened. To show that a grammar is ambiguous, we all need to do is find a terminal string that is the yield of more than one parse tree. Meaning, when we say it is ambiguous, if you find the parse tree that is giving two different values or it has different yields, you can say. So there are two different yields for a parse tree. We say that is an ambiguous situation, and we'll see one of the example of that. Since a string with more than one parse tree usually has more than one meaning. As I said, if you have multiple number of parse tree means you have multiple number of meanings are also there. We need to design unambiguous grammars for compiling applications. Let us say you write a program to a computer saying that A is equal to B plus C. So to understand A is equal to B plus C, let us say the computer derived it or it did the computation in such a different way that the meaning become different. Instead of A is equal to B plus C, it did something A is equal to B minus C or A plus B is equal to C, some different interpretation. So that means there is an ambiguity because it interpreted your instruction in a different way. So the meaning became different. So in order to have that, you should have an unambiguous grammar, meaning an expression should have only one meaning and there should be only unique parse tree. So that parse tree will yield the actual intention of writing the expression, and that has to be understood by the compiler. So that is what it says. Since a string with more than one parse tree usually has more than one meaning, we need to design unambiguous grammar for compiling applications, or to use ambiguous grammars with additional rules to resolve the ambiguity. Or if you are making this, you are allowing your compiler to work with this ambiguous parse trees, you should have some features or additional rules that can resolve the problem of ambiguity. So there are two things. Either you make a unambiguous parse tree, that is the final outcome, or you allow to go for an ambiguous parse tree, but again this ambiguous parse tree has to be corrected or has to be refined by some additional rules into that, so that your ambiguity is resolved. We'll see what exactly is this kind of ambiguity and how it can be resolved. Suppose we used a single non-terminal string and did not distinguish between digits and lists. As in a regular example, we could have written the grammar like this. String is nothing but a string plus string, or a string minus string, or is 0, 1, 2, 3 up to 9. We could have written any of this form. Why we wrote string plus digit or string minus digit? Why you wrote that? We could have written in this way. So what will happen by this? Merging the notion of digit and list into a non-terminal strings makes superficial sense, because a single digit is a special case of a list. This is what we studied, right? So if we are using a list means what we are saying, it is also a digit. And if we don't use that, the notion of digit and list into non-terminal strings. Non-terminal strings means the strings defined by the user, right? Has no meaning, or you can say it doesn't make any sense. So what we did, we mentioned your list is equal to list plus digit, or you can say string is equal to string plus digit, or string minus digit, or digit can have the form of all this. This is what was required to remove the ambiguity in the parse tree. Now you see, we'll see the parse tree with ambiguity, how it happens. We had 9 minus 5 plus 2, right? So what you have done is, this is the one we have already done, right? Now the ambiguous tree, you can see. Here what it comes? First 9, then minus 5 plus 2. That means what it does, your equation was 9 minus 5 plus 2. Either I will do the 5 plus 2 first. So 5 plus 2 is how much? 7. Then I will do 9 minus 7 is 2. That is one result. Second result is, I will do 9 minus 5 first, which is equal to 4. Then 4 plus 2 is equal to 6. That means you understand your equation or expression, which is nothing but 9 minus 5 plus 2, can have two values. Either it can give a value of 2 or it can give a value of 6. Tell me, is that possible? Can a single expression have two values? Either it can be, hello? Yeah, anyone wants to say something? Okay, so that means when we say that there is a parse tree or there are two, for a single equation or single expression, we cannot have two parse trees. And these two parse trees, you can see they are having different values. That means this one gives the result equal to 2, this one gives the result equal to 6, which is absolutely ambiguous. Right? So you see, this has been gone deep into left, this has gone deep into right, because the compiler interpreted both of them in a different way. That is what is the reason why both of them have the different results or are having ambiguous yields. We'll see that. The above figure shows that an expression like 9 minus 5 plus 2 has more than one parse tree with this grammar. As I said, it has got two parse trees. The two trees 9 minus 5 plus 2 correspond to the two ways of parenthesizing the expression. One is parenthesizing 9 minus 5, another is parenthesizing 5 plus 2. If we are parenthesizing 9 minus 5, the result is 6. If 5 plus 2 is parenthesized, the result is 7. That means for the same expression, we are getting two different results, which is ambiguous. So now the second parenthesization gives the expression that unexpected value 2 rather than customary value 6. Actually, it should be 6, but because of this wrong interpretation, we got the value of 6. Sorry, we got the value of 2. That is what is the ambiguity in the parsing the value or ambiguity in making the parse tree. Right? So why this ambiguity occurred? Because the lexical analyzer or the compiler could not understand which operation has to be done first. 9 minus 5 should be done first or 5 plus 2 should be done first. Because it could not understand which operator is associated with which operand. What are the two operators here? One is a plus, another is a minus. There are two operators. What are the operands? Three operands. One is 9, then is 5, then is 2. So with two operators and three operands, the compiler could not understand to which operator it will associate which operand. That is why it did the ambiguous parsing. So if the compiler understands what is the association of a particular operator with an operand, then it could have done it easily. So to understand that, we will see the associativity of the operators. Meaning an operator when given in an expression, we should understand that the operator is associated to its left side or to its right side. So we'll see that now. Associativity of operators. By convention, 9 plus 5 plus 2 is equivalent to the same remains same, right? 9 plus 5 is 7 plus 2 is equal to 9 plus 5 is 14 plus 2 is your 16. And 9 minus 5 to 2 is equivalent to 9 minus 5 is 4 minus 2 is 2. So there is no ambiguity in this. This is absolutely clear cut value. When an operand like 5 Here, let us say the operand like 5 has operators to its left and right. Remember that 9 minus 5 plus 2. The 5 has two operators. Left side is the minus, right side is the plus. So it has two operators to its left and the right. Conventions are needed for deciding which operator applies to that operand. Meaning, for 5, which one is applying? Minus 5 should be done first or plus 2 should be done first. If this is clearly understood by the compiler, there will be no ambiguity in the interpretation. So how that is being done? We say that the operator plus associates to the left because an operand with plus sign on both the sides of it belongs to the operator to its left. Meaning, if a operand has got two signs, one is plus and the minus, then it is usually assigned to the left side of sign first. So it says that the operator plus is associated to the left. What is there in the left? 9 minus 5 plus 2. So what is there in the left of plus is 5. So this plus is associated to the left because this operand with plus sign on both sides of it belongs to the operator to the left. And in most programming languages, the 4 arithmetic operations like your addition, subtraction, multiplication, and division, they are usually called the left associative. Meaning, usually these symbols are associated to the left side. So if we say 5 minus 5, then 5 minus 2, then minus is associated to the left value, that is 5 minus. If we say 3 into 8, that means the into is initially associated to the left value, or that is equal to 3. This is how your associativity of the operator with the operands are taking place. But there are certain values or certain scenarios where the operator is associated with the right values, or they are called the right associative. So there are some common operators such as exponentiation and the equal to sign or the assignment sign. They are usually right associative. We'll see how. The assignment operator is represented as an equal to symbol in C, and its descendants is right associative. Meaning, the expression A is equal to B is equal to C is treated in the same way as the expression A is equal to bracketed B is equal to C. So because this is right associative, always the operator, the operator is associated with the right value. So that is what it says, it right associative. Or for an exponential e to the power 23. So e to the power 23, meaning this operator e to the power 23 is a right associative for the operand. So that is why there are certain things which are always left associative. There are certain operators which are right associative. So strings like A is equal to B is equal to C with a right associative operator are generated by the following grammar. We'll see how these associative operators are generated. If that is generated, then the computer can do non-ambiguous equation formation or non-ambiguous parsing of the expression. So to have the right associative operator, usually right can have the form of letter is equal to digit, or it can have simply right can have the value of letter. So if it doesn't want to add to the digit, or if it is having only the string values, then it can have the production as Right can have the form of letter is equal to digit or is simply letter. That will be done. Whereas letter means or letter can have the form of A, B, C up to any value Z. This is what is your right associative rule. So now we'll see what is the parse tree to the left and what is the parse tree to the right. So the parse tree for left associative goes down to left and the parse tree with right associative goes down to right. Now you see this is left associative, meaning 9 minus 5, this will be 9 minus 5 minus 2 or whatever maybe. They are all these operators plus, minus, multiplication and division. They are all, as I said, left associative. So left associative means the tree that has been designed or the tree that has been formed, it goes down to the left. Similarly, when the equal to symbol is there, so or the exponential values are there, then they become the right associative. And if it is right associative, then the tree goes down to the right. So A is equal to B is equal to C. This is what is the expression or right associative of the equation, you can say. This is what is the difference between a left associative and right associative. So your operator will decide what kind of associativity it will be. If it is a plus, minus, multiplication, division, definitely that is going to be a left associative. If it's the equal to or exponential something, it is going to be the right associative expression. Okay, so before we go for the precedence of operators, I'll just take a 5 minutes break. If you want to have some water or something, just go and quickly come back within 5 minutes.
So students, wait for 5 minutes. Ma'am will join soon. Okay.
and star apply to occurrences of the same operator. So they do not resolve this ambiguity. Meaning, whatever rule for plus is there, the same rule is for also star. What is the rule? If it is there, it is always left associated. As I said, plus, minus, multiplication, division, both are all got left associativity. If it is left associativity is there, then for plus and star, both are left associated. In that case, the ambiguity cannot be resolved. So how we can work on this? So rules defining the relative precedence of operators are needed when more than one kind of operator is present. So what it says? The precedence of operation or relative precedence of operator will be required so that the operators present can be distinguished and the precedence can take place, or that can take the role by the computer to execute or to compute the equation. So what it does in the precedence of operators, we say that star has got higher precedence than plus if star takes its operands before plus does. We know that as per the BODMAS, what we have studied is star has got higher precedence than the plus because star takes its operands before plus takes its operands. That is what is happening. So here also in ordinary arithmetic, multiplication and division have the higher precedence than addition and subtraction. We have studied that. So therefore, in this case, 5 is taken by multiplication first because we have two operators here. One is 5 and one is plus, another is the star or the multiplication. So if multiplication is taken first, this operator is left associative. So being the left associative, it takes the 5 first before plus takes the 5. So in what happens? Therefore 5 is taken by star in both the cases of 9 plus 5 star 2 or 9 star 5 plus 2. In any of the cases, 5 is taken by the star first. That is, the expressions are equivalent to 9 plus parenthesis 5 cross 2 and 9 cross 5 parenthesis plus 2 respectively. So this is what is the precedence has been taken by the star operator. So if we see an example of this precedence of operators, we will see that a grammar for arithmetic expressions can be constructed from a table showing the associativity and the precedence of operators. Probably it is there. We'll see that later. Okay. So to start with the 4 common arithmetic operators, what are the 4 common ones? The plus, minus, multiplication and the division. A precedence table can be designed which will show the operators in order of increasing precedence. Meaning there should be a table which will guide the compiler saying which will have the first precedence, that is the division or multiplication. Then the next precedence will be addition or subtraction. That way it has to be mentioned. So operators on the same line have the same associativity and precedence. For the left associative, we know plus and minus have the same precedence and same associativity. And multiplication division has got the same precedence as well as same associativity. They lie in the same layer of precedence. So how in this scenario, how the non-terminals will be created? You remember non-terminals, right? Non-terminals are the expressions or the keywords that is not keywords. Keywords are the terminals or the tokens are the terminals. Non-terminals are the expressions or the variables or identifiers, you can say. So how they will be created in this case? So we create two non-terminal expression and term. These are the two identifiers, or we say these are the two non-terminals for the two levels of precedence. If we take two levels of precedence, one for the plus and minus and another for the cross and multiplication and division, then we create two non-terminals. That is, one is expression and another is the term. And an extra non-terminal we are creating, that is factor, for generating the basic units in the expression. So we are taking three non-terminals. One is expression, another is term, and another is the factor. We'll see how the precedence of operators can be handled by the compiler or by the lexical analyzer. So the basic units in expressions are presently the digits and parenthesized expressions. So we have something now. One, we have the digit, and we have another two digits in a parenthesis. What we call is an expression. So it says factor, there is a production now. This production has been created. So what is this production says? The production is the head is the factor and the body is either the parenthesis. So this is how your production is. Now we'll see. Now consider the binary operators multiplication and division. Why we say this is binary operator? Can anyone answer to this? Why these operators are called binary operators?
Ma'am, because they require two operands.
Very good. So because any of these operators, they need two operands to be worked on, we say they are the binary operators. Now let us consider any of these binary operators and that have the highest priority. We know that. Since these operators associate to the left, we know that plus, minus, multiplication, division, they are all left associated. So because they are the left associated operators, the productions are similar to those for the list that associate to the left. So what happens now? Your term is, this is our production, you can say. The term can have the form of term into factor, or it can have the term / factor, or it can be simply a factor. Like if you remember, the list can have list plus digit, list minus digit, or list digit. The similar way, it can have the term into factor, term / factor, or simply term is a factor. This is the rule for your production formation for this operator star and slash, having the highest precedence. Now similarly, expression generates the list of terms separated by the additive operators. What is that? Expression can have the form of expression plus term. What is expression? It's a parenthesized term, right? Parenthesized expression. Sorry. Or it can have expression minus term, or it can have only term. So what are the things we generated? We had the non-terminals. One is expression, another is term, another is factor. So here we frame the rules for with factor and term, and for plus and minus. And now for minus and for star and the slash, and for plus or minus, we have the new production as expression can be expression plus term, expression minus term, and expression can be a simple term. So what will be the resulting grammar then? The resulting grammar will be expression can be either expression plus term, the first one, or expression minus term, the second one, or the simply term. And considering the highest precedence values or operators, term can be term cross factor, or torn slash factor or simply factor. And what is a factor? Factor is nothing but either a digit or it can be an expression. So now you understand how the production can be generated or how the parse tree can be generated. So if any value is given, that will be first considered as a factor. And if that is a factor, then putting the factor into this form, first the term will be generated. And once the term is generated, the term will be put in the appropriate place so that the expression can be generated. Now, once the expression is, that means your highest precedence goes to your star and the slash or the multiplication and division, and the second precedence goes to your plus and the minus. This is what is explained here. With this grammar, an expression is a list of terms separated by either a plus or minus sign, and a term is a list of factors separated by a cross or a division sign. Notice that any parenthesized expression is a factor. So with parenthesis, we can develop the expressions that have arbitrarily decreased. So when I say this factor can be an digit or an expression, so whatever expression you say here can be also this plus and minus thing. If there is any plus and minus thing, that will be considered here first within parenthesis. That means your bracket is done first, then your of and division is done first, then your addition and subtraction. So you can say automatically your BODMAS is implemented into this context-free grammar or this grammar, so that your expression is understood for the precedence of operators. Is this clear now? So if you have either a simple plus or minus, you can have the set of rules for the framing or formation of the grammar. If you have the star and the slash or the parenthesis, so to apply the BODMAS onto this, you can have the precedence of operators, and this is how you frame the compiler is designed or compiler is instructed with this set of grammars so that it compiles the computation accordingly by taking the precedence of the operation. Now we'll see more example on this to make it very clear. So the keywords allow us to recognize the statements. Since most statements begin with a keyword or a special character, that we know. So this is not a much of importance of this. Now exceptions to this rule include the assignments and procedure calls. So till now what we did is only the arithmetical operations, plus, minus, division and multiplication, and we applied the precedence of the operators there, but we didn't do anything for a procedure call. Procedure call means calling a subroutine, calling a module. So in that case, what it will do? What will be the precedence? What will be done first? And another is the assignment. So how that can be done? For example, you have a statement called statement is can have the, this is a production, right? Statement can have the form of ID is equal to expression. Any identifier, I can say, any identifier, which is a non-terminal, of course, any identifier can have the equal to the expression. This is an assignment. Or if the expression is true, then there will be some statement. Or if the expression, then some statement, else another statement. Or it can have while the expression, then some statement. Or do some statement while the expression is true. Simply a set of statements. So these are the different kind of languages or different kind of instructions you give to the computer. Do you or not? You give like this. So till now what we studied only the arithmetic operations and their precedence of operation, how it takes place. But in general, when you write a program, it contains like this similar kind of statements like this. These are the different examples of the statements that visually we write in the program. So how the computer or the compiler understands these languages, these statements, how it interprets. And another is statement can have another form of, or can have the production like statements, then statement. This can be also possible, or it can have simply epsilon, means no terminal, empty terminals you can say. Empty terminal means no keyword is there. Absolutely there is no keyword. This could be also possible statements. So these are again the different kind of statements that are entered into the compiler, and we'll see subsequently how the compiler handles those kind of things. But for now, we'll study about the syntax directed translation. So slightly we'll go deeper into the things, how each of the statements are understood, how each of the statements are being evaluated by the compiler. So the syntax directed translation is done by attaching rules or program fragments to productions in grammar. Meaning, this is what is a task you can say, syntax directed translation. So this translation is done by attaching a set of rules, or set of rules means a program you can say, program fragment to productions in a grammar. We know what is a production, right? So if you go on adding the rules or attaching the program fragments, then automatically we'll land into a syntax directed translation. We'll see how that is being done. For example, consider an expression generated by the production. Expression can have the form of expression 1 plus term. Now here two things, one is expression, another is expression 1. Actually both are almost same, but this expression 1 is just to indicate that there is another instance of expression, meaning it's like t is equal to t plus 1. What do you mean by that? What is the difference between t and the left t and the right t? Left t is the upgraded value of the right t. Sorry, the right t will be incremented by 1, then it is allotted to the left t. So though it is expressed with t is equal to t plus 1, but it has actually the value of t at two different instances. So similarly, here also it says expression can have the value of expression 1 plus term. So here expression is the sum of two sub-expressions. One is the expression 1 and another is the term. So when these two sub-expressions are concatenated or added, it gives to a new production head, that is the expression. So we can translate expression by exploiting its structure. Now how this expression is translated? First is translate the expression 1 of the sub-expression. Then you translate the term, the next sub-expression. Then you handle the plus operator. The plus operator can be simple arithmetical addition, string addition. This can be file addition, can be anything. So once this is handled, we will get this head or the whole of the production as the expression. This is what is the translate expression is being translated. So when the compiler works on this, or the lexical analyzer works on this, it first translates the first sub-expression, it translates the second sub-expression, then it does the combination of these two to translate the final expression. So there is, to understand more details of this, there are two concepts that we must know related to this syntax directed translation. One is the attribute and another is the translation schemes. So what is attribute? We'll see first. So any questions by now, so that I can, before I go for the next things, I can take one or two very quick questions. If you have any questions, you can ask me now.
Ma'am, as such, no questions. You can continue.
Okay, thank you. So now next is the attributes. The concept of attribute, what it says, an attribute is any quantity associated with a programming construct. Examples of attributes are the data types of expression. You know, right? What is the attribute of anything means? Those are the characteristics, or you can say the features, or associated with any term or expression. That is what is the attribute. So examples of the attributes are the data types of the expressions, the number of instructions in the generated code, or the location of the first instruction in the generated code for a construct, or among many other possibilities. So attribute can be anything. Like if you create a data can have multiple attributes, like what is the type of the data, what is the size of the data, what is the memory location of the data. So a data has got different attributes. Similarly, here also, when you talk about any quantity or any component entity in the programming, we talk about the attribute. It can be any of these values. Since we use the grammar symbol means either the terminals or the non-terminals to represent the programming constructs, we extend the notion of attributes from constructs to the symbols that represent them. So what we understand here is only from instead of this, these two are the constructs called the non-terminal and terminals are called the programming construct, and we apply or we extend the notion of the attribute from the constructs to the symbols that represent how these terminals and non-terminals are being represented. That is what is called the attribute as of now. Another is the translation schemes. A translation scheme is a notation for attaching the program fragments to the production of grammar. And the program fragments are executed when the production is used using the syntax analysis. That means during the syntax analysis, your whole of the production is taken as the input for the syntax analysis, and then this production is partitioned into or fragmented into small, you can say modules or small grammars, and then it is being executed. So that is what it says, the translation scheme. In the translation scheme, the program fragments are executed when the production is used during the syntax analysis, and the combined result of all these fragment executions in the order induced by the syntax analysis produces the translation of the program to which this analysis or synthesis process is applied. That is what is the different translation schemes. Though it doesn't explain much on this, we can go for the further things, so that just to understand, these are the two concepts related to your attributes and the translation schemes. So then we'll go for the notations. As I said, here you see how the notations are being done. Translation scheme is a notation for attaching the program fragments to the production of the grammar. So what are the different notations used in the programming for understanding an expression or for understanding an equation? One of the notation is the postfix notation. If any of you knows about postfix notation, if you will understand why for a single expression you have three different notations. One is infix, another is prefix, another is postfix. So when we write a program, we write an expression, we usually write in the infix notation. 5 plus 3 minus 2. This is an infix notation. Your operators are put in between two operands. That is the infix notation. But the computer does not understand the infix notation because of certain interpretation issues or problems. What it understands? it understands the prefix or the postfix. So we'll see what is this postfix notation is and why it is so important. The postfix notation for an expression E can be defined inductively as follows. First is, these are the rules of postfix notation, you can say, or you can say the steps for writing in a postfix notation. First is, if E is a variable or a constant, then postfix notation for E is E itself. If I say a expression is equal to E, that means there is only one variable or one constant. What will be the postfix notation? There is nothing, no operator, nothing is there. So the postfix will be the E itself. If I say X is equal to A or something, only the expression contains only one identifier A, the postfix notation will be A also, because it doesn't have anything to be added or pre-added. Then, if E is an expression of the form E1 operated E2 or E1 operator E2, that means there is an operator OP and there are two operands E1 and E2 in any expression, then the operator OP is a binary operator, and then the postfix notation of E is just 1 minute, students. So what it says, if E is an expression of the form E1 and E2, then the operator is any binary, and the operator is any binary operator. As you said, there will be two operands. Then the postfix notation for E is E1 dash, E2 dash, and the operator goes to the end, where E1 dash and E2 dash are the postfix notations of E1 and E2 respectively. Meaning, it can happen that E1 dash can be same as E1 or it can be different than E1. Similarly, E2 dash can be E2 or it can be different. But what the objective is or the purpose is, if these two are the two expressions, binary expressions, and the operator is in between them, then the postfix notation will be the operator goes to the end of the operands. That means the operands comes first and the operator goes to the next. And the third condition is, if E is a parenthesized expression of the form E1 in parenthesis, then the postfix notation for E is the same as the postfix notation of E1. Meaning, if it is a parenthesis, then within the parenthesis, the same expression or same postfix notation will be there. We'll see an example to make it very clear. What it says, the example is, see, here the postfix notation for parenthesis 9 minus 5 plus 2 is, first is the parenthesis comes. So what is the operator here? Minus. And this is the infix notation because two operands and in between there is the operator. So this can be written as 9, 5 and the OP or the operator goes to the right side or it goes post the operands. That is why this is called postfix. So 9, 5 minus becomes the first postfix of the parenthesis. Then comes the whole thing will be considered as now expression E. So now this comes E plus 2. So what will be the expression or what will be the postfix notation? This E, then 2 followed by the operator. So what is the E now? E is 9, 5 minus. Then the next operator is 2. The next operand is 2 followed by the operator plus. So this 9, 5 minus 2 plus is the postfix notation of 9 minus 5 plus 2. This is what is the postfix notation. That is, the translations of 9, 5 and 2 are the constants themselves by rule 1. Then the translation of 9 minus 5 is 9, 5 minus by rule 2. The translation of bracketed 9 minus 5 is the same by rule 3. Having the translated the parenthesized sub-expression, we may apply the rule 2 to the entire expression with 9 minus 5 parenthesized in the role of E1 and 2 in the role of E2 to get the value of 9, 5 minus 2 plus. This is what is the explanation of converting the infix 9 minus 5 within parenthesis plus 2 to the postfix notation. Why we say this is infix? Because the operator is in between the operands. Why we say that is postfix? Because the operator is post the operands. Why we say something prefix? Because the operator is prior to the operands. That is how the notations are explained. Similarly, in another example, we'll see how the same postfix notation is changed because your parenthesis has been changed now. You see, here now in this case 9 minus 5 plus 2 is taken as in the parenthesis. So what will happen? Because it is in the parenthesis bracketed, so this parenthesis will be operated first. So what will happen now? The postfix notation of 5 plus 2 is 5, 2 plus. So this will be considered as E1 as 9 minus E2 as 5, 2 plus. So when that will be considered as in the presented in the postfix, it will be 9, 5, 2 plus. Then this minus operator, this binary operator will come to the end. That is what is explained here. That is 5 plus 2 is first translated into 5, 2 plus. And this expression becomes the second argument of the minus sign. So the answer will be 5, 2 plus 9, 5, 2 plus minus. So here 5, 2 plus comes first, then 9, 5, 2 plus minus comes next. This is what is your postfix notation for the expression 9 minus 5 plus 2. So these expressions are, mentioned in this steps of postfix notation. No parentheses are needed in postfix notation. You see, once this comes into the once it comes into this postfix notation in both the cases, this one and this one, we are not putting any parentheses because parenthesis has no value here. Once when it will be analyzed or scanned by this your lexical analyzer, automatically this will be considered which one will be operated first, which one will be operated next. Because that's what it says. No parentheses are needed in the postfix notation because the position and the arity is the number of arguments of the operators permits only one decoding of a postfix notation. The trick is to repeatedly scan the postfix strings from the left until you find an operator. You see, let us work on this one. Any of this. Let us say 95 minus 2 plus. This is the postfix notation. How the compiler executes this? It scans the whole of the string till it gets the first operator. So it scans 9, it scans 5, then it finds the minus operator here. This is the first operator. It comes, it comes first. So what happens? Repeatedly scan the postfix string from the left until you find the operator. Then look to the left for the proper number of operands. Now in this case, what is the proper number of operands? 2, right? So, and group this operator with its operands. So once this minus comes, you look back or go to the left with the number of operands. Because this is a binary operator, so number of operator will be 2. So then you take 2 operators, 9 and 5, and work upon this. So 9 minus 5 will be operated first. That means this is operated first, your parenthesis is operated first, understood? Then again is go on scanning to 9 minus 5, and here it will be 4, 2, then the second operator comes. When the second operator comes as the plus, it goes, looks back or looks left. One is 4, another is 2. So now 4 plus 2 will be added here, that is 6. So whole of the operation is being executed here. Now you understand why the infix notation is converted to the postfix notation for a compiler, because in this it is difficult for a compiler to do the compilation and understand the things. Rather, it is easier here by simply scanning the string of characters and executing the operation on it. This is what is being explained here. Group the number with this, evaluate the operator on the operand and replace them by the result. Then repeat the process, continuing to the right and searching for the next operator. So the process is continued till the last operator comes, and accordingly this operator is executed over the previous 2 operands if it is a binary operator. If it is an operator that needs 3, then accordingly 3 inputs will be, 3 operands will be searched, and that will be worked out. This is how a postfix notation is executed by a compiler. Here is another example, a postfix notation, 952 plus minus 3 star. So if you can work on this, it will be easier. Just see how it does the execution, or how this postfix notation is executed. Scanning from left, we first encounter the plus sign here. So what it does, looking to the left, we find the operator 5 and 2. So this is executed over 5 and 2. 5 plus 2 is 7. So now here 9, 7, minus. So next operation comes as minus. So when the minus comes, the previous 2 operands are 9 and 7. So there 9 and 7 will be answer will be 9, 7 will be 2. So now 2 and 3 will be, then the third operator is star. So 2 cross 3 will be 6. So this is how the result is explained. So now the multiplication sign applies to 2 and 3, giving the result of 6. This is how your postfix is executed. Okay. So till now, if there is any question, I can take, or we can have a break of 5 minutes. Then again we can start. So you can have, if you want to have some water or something, just go and quickly come back within 5 minutes. In terms of the grammars, because grammar means what? Grammar is nothing but your syntax, right? and any compiler has the syntax analysis or syntax analyzer who does the grammar or who does the translation. So everything has to be expressed in terms of grammar because that grammar can only be understood by the compiler. So we associate the attributes with non-terminals and the terminals. So any attribute that we will study will be associated with the terminals and the non-terminals. Then we attach the rules to the productions of the grammar. Productions already we know, and these productions will be attached with certain rules so that that rule is within the scope of the grammar, you can say. These rules describe how the attributes are computed at those nodes of the parse tree where the production in question is used to relate a node in its children. So whatever rules that we will associate with the production will describe the attributes, and these rules are computed at the nodes of the parse tree because you have the different nodes in the parse trees, right? Where the production is used to relate a node to its children. How the interior node or the root node or any node is associated with the children will be described by these rules. That is what is called the synthesized attributes. So a syntax directed definition associates with each grammar symbol a set of attributes. So when you will use any grammar symbol now, we'll use a set of attributes for the symbol, and with each production a set of semantic rules. Till now we are writing the productions with the start symbol at the or the head at the left side of the production and the body at the right side. That was the only rule we are following. But now we'll see the set of a semantic rules for computing the values of the attributes associated with the symbols appearing in the production. So every symbol in the production that will be used will be associated with a certain rule. That is how slowly we are progressing for enhancing the understanding of the compiler for every instruction in the program. So these attributes can be evaluated as follows. For a given input string X, construct a parse tree for X. Let us say the production is given like this. A is a production of X, Y, Z. So now you construct the parse tree for this production. Then apply the semantic rules to evaluate the attributes at each node in the parse tree. Of course, this is a simple parse tree, so there is only one node, that is root node. But when you have the multiple nodes in the parse tree, like 9 minus 5 plus 2, that equation, in that kind of parse tree, apply the semantic rules to evaluate the attributes at each node in the parse tree. How? Let us say, suppose a node n in a parse tree is labeled by the grammar symbol X. Let's say consider any parse tree. There is a node n, and you label that node by a grammar symbol X. We write X dot A to denote the value of attribute A of X at that node. Meaning, if I say X dot A, it says the attribute of X at that node. What is the attribute of X? Attribute is the A, let's say data type is an attribute, right? So what is the data type of X at that node will be mentioned. That is what X dot A, the attribute of X. Now, a parse tree showing the attribute values at each node is called an annotated parse tree. So, but till now, what we studied is a simple parse tree where it contains all the symbols, the terminals, the non-terminals, the start symbol, and the tokens, everything. The production is shown in the parse tree. But when the parse tree nodes are identified with its attribute, that becomes an annotated parse tree. So every node has its attribute, and that attribute is mentioned as the node dot A. We'll see. Now see, same 9 minus 5 plus 2. This is the parse tree, simple parse tree we have already said. So what this parse tree had earlier, we had the expression, we had then the digit and everything was there. Now you see this has got an attribute dot t, expression dot t, expression dot t. This is everything is being written. So what it says, here the digit was there, earlier there was a digit here, right? So this term dot t will be explained as this is a digit. So this is a digit within quotation, digit. Here this is a negative sign. So this is not an interior node, so leaf node. So there is no attribute for this, so we can leave it like this. Now for this node x, or what you say, the x dot a, or the term that t stands for 5. This is a value 5, and this is a value similarly 2. Now coming to this interior node, what will be the value here? The postfix notation of this. This will be equal to 9, 5 minus. This is the attribute here, the postfix notation, that is 9, 5 minus. And here the term is 2. So what will be the notation, for this annotated parse tree? Here expression dot t will be the postfix notation of 9, 5 minus this plus and this 2. That will be equal to 9, 5 minus 2 plus. This is what is the notation here. So the whole expression, whatever you studied earlier, was a simple parse tree, but now this parse tree along with its attributes has become an annotated parse tree. We'll see what is the annotated parse tree. This figure shows an annotated parse tree for 9 minus 5 plus 2 with an attribute t. T is the attribute associated with the non-terminals, expression and the term. You will see here, for all the expressions and for all the t's, the attribute t has been added. So the value 9, 5 minus 2 plus of the attribute at the root is the postfix notation of 9 minus 5 plus 2. This is the, so what is the attribute here? It is the attribute is the postfix notation of 9 minus 5 plus 2. So here you will see all these notations, the t stands for the postfix notation. So for 9, what is the postfix notation of 9? Simple 9. Similarly for here also, the postfix notation is, because there's a single child, so only 9. But here it has got 3 terms, so the postfix notation is 9, 5 minus. That way it goes. So t here is the attribute stands for the postfix notation, and that is being changed, or that has been mentioned in the annotated parse tree. What is your a variation of your standard parse tree. Now, an attribute is said to be synthesized if its value at a parse tree node n is determined from attribute values at the children of n and at n itself. Meaning, your attribute is synthesized if its value at a parse tree node n is determined from the attribute values at the children of n and at n itself. It is, for the case, it has not been synthesized because the value carries roots till the root. So synthesized attributes have the desirable property that they can be evaluated during a single bottom-up traversal of a parse tree. Sorry, the synthesized attribute here, what it says, if you go here also, this can be evaluated with this value. So everywhere the evaluation of the parse tree is being done, and that is why we say this is synthesized attribute of the of the parse tree. Now you will see that this table will come later. Just having the rules, we'll see the production. Earlier the production, the initial production was expression, which is nothing but your expression 1 plus term. Then expression is expression 1 minus term. Then expression is term, and term will be for any value 0 to 9. The semantic rules for associated for this is for the postfix notation of every digit will be from 1 to 9 will be as it is 1 to 9. Sorry, 0 to 9 will be as it is 0 to 9. Then this expression T will be same as your term T, because the postfix notation of term will be the postfix notation of expression. So whatever will be the postfix notation, that will come to the expression T. And this expression T is nothing but your expression 1T. Then this is a concatenation. We'll come to this, what this concatenation is. Then the term T, whatever digit you take from here, concatenation with the operand, with the operator. And similarly, this one comes here. So with this semantic rules, your productions are being converted to this. Now you see, this is the syntax directed definition for infix to the postfix translation. What is syntax directed definition? We'll see now. For example, the annotated parse tree is based on the syntax directed definition as above for translating the expressions consisting of the digits separated by the plus or minus signs into the postfix notation. And each non-terminal has a string valued attribute T, that is a string valued attribute that represents the postfix. As I said, T represents the postfix notation for the expression generated by that non-terminal in a parse tree. And this double bar is nothing but a semantic rule. If you remember, the semantic rule is associated with every node, as I said in the earlier slide. So this is the semantic rule, is the operator for string concatenation. Meaning, you'll see here, when this 9, 5 and minus are being operated, these are all the string concatenation. So this string concatenation comes because we are associating the attribute with this interior nodes. So with that, it takes the string concatenation. So the postfix form of a digit is the digit itself. As we studied, postfix notation of 0 is 0, 9 is 9, 5 is 5, it's all the same. That is, the semantic rule associated with the production term can have the form 9 defines term T to be 9 itself whenever this production is used at a node in the parse tree. That means if term is 9, then the postfix notation of term will be 9 only. So any value between 0 to 9, that postfix notation will be the same digit. The other digits are translated similarly, like 0 to 8. As another example, where the production expression can have the value term is applied, the value of term T becomes the value of expression T. As we saw here, term T becomes expression T now, because expression can have the value form of term. So the notation, postfix notation of term will be the postfix notation of expression. That is what it says. And the production expression can have the value of expression 1 plus term derives an expression containing a plus operator. So the left operator plus given by expression 1 and the right operand by term. So the combination will be expression 1 dot T plus term dot T, and that will be equal to your expression dot T, which is the postfix notation of these two expressions. This is what is the semantic rule is. Expression dot T will be expression 1 dot T concatenated by term dot T concatenated by the operand plus. So this will be equal to 9. This is 5 plus. So your value will be 9, 5 plus. This is how your postfix notation is generated. So this semantic rule is associated with this production constructs the value of the attribute expression.t by concatenating the postfix forms expression.t and tom.t of the left and right side operands, and then appending the plus sign. This is what is being done. So this rule is a formalization of the definition of postfix notation. This is what is your how a postfix notation is generated by the compiler or by the syntax analyzer or by the parser. So now you understand, if you have given an equation, if you have given an expression, the expression first your productions are set, then the productions are associated with an attribute, then these attributes or what you say the semantic rules, then according to the semantic rules, these attributes are concatenated to generate the postfix notation of an infix expression given as the input to the equation. This is what happens with in the expression. So till now what we studied in today's class is about the different kind of operators, the precedence of the operators, and how your grammars are being framed for different productions and all, and how this infix is converted to postfix mathematically, and in terms of grammar how that is being applied with the semantic rules, and how these semantic rules convert the infix notation to the postfix notation. So I think with this I can take some questions. If you have any query, you can ask me, and the rest of the things we can continue in the next class. Professor Chakravarti, are you there?
Yes, ma'am.
Okay. So
Students are requested that if anyone has any question, please ask, ma'am.
I think they are getting, exhausted for this long hour. That is why I'm trying to give a 5 minutes break for some between, so
Yes,
that at
ma'am.
least they can get some freshened up. But it's okay. If they ask any query anytime also, I'll be able to answer. Should not be an issue.
Ma'am, yet now everything is clear.
Everything is clear?
Yeah, ma'am.
Great. Good. Because Professor Chakravarti, I'm actually going very slow because so that they should understand the basics. So
Yes, ma'am.
once this parsing and everything are clear for them, then it will be easier for them to understand what the lexical analysis does, what the semantic analysis does. Instead of knowing this basics, suddenly if I go there, there will be no point. So
Yes, ma'am. Because it is necessary for basics.
Yeah,
so,
yeah.
There is no
semester.
rules and regulation to complete the syllabus, but
Okay.
only we have to basics are the clear.
Yeah. If they are clear with the basics fundamentals, then there should not be any issue. They can understand the rest of the things also.
Yes, ma'am.
So tomorrow there is a break, right?
Yes, ma'am. So today the session ends here.
Yeah.
Okay,
For
ma'am.
today it's over.
Okay, ma'am. So the students are requested to join again next day at 18th. We will be back at 2:30 p.m. So thank you, ma'am. Thank you everyone for joining the session, and thank you, ma'am, also.
Thank you. Thank you. So we'll see on Friday then.
Okay, ma'am.
Okay. Thanks a lot. Thank you.
Excuse me, sir.
Okay.
So, on 18th, will we continue this?
From 18th to 2:30 p.m. It will be day 4.
Okay. Okay, sir. Means the continuation of compiling this.
Yes, ma'am. Yes.
Okay. Thank you so much, ma'am.
Okay. Thank you. Thanks a lot. I think there was a question. There is something students. Okay. Thank you. So I'm leaving the main meeting then.
Yes, yes, ma'am.
Okay, thank you.